Okay, so this is the 7th review section. And we're going to get started with problem 1 about bond enthalpies, okay? So as far as I remember, yes?
Do you mind recording, please?
I'm recording it.
Oh, okay, awesome. Thank you.
I am recording it. I always record it, every single time. Okay. For these bond enthalpies, what's the rule? How do we calculate these things? So there's table 6.1 in the book, right? It lists, what does it list? Can somebody? Yeah, what does it list? It lists how much energy, right?
Yeah,
It
it's the energy that it requires to break or form a bond.
To break or form a bond. So, okay, yes. So generally all the bonds, right, it always costs energy to break a bond and releases energy to make a bond. So what's the sign of those numbers in the book? Sometimes it's tabulated in one direction, in terms of forming the bond, and then they are negative, right, because then energy is released. But probably the numbers in the book are positive, aren't they? So if they're positive, it means that it goes in the direction of breaking the bond.
Right.
Okay? So if you break the bond, you put in energy. So what it means what you need to do if you use those numbers is you take all the bonds which are broken minus all the bonds which are formed, right? And then if the overall energy like this is negative, then it's an exothermic reaction, okay? Because the energy is negative, energy is released overall. And if it's the other way around, right, and it's overall positive, then it's an endothermic reaction. Make sense? So let's try. Who has those numbers? We basically have to, so first of all, which bonds are broken? Let's see which bonds are broken. We can write them down. Like a carbon Ci bond, right? The carbon-iodine bond is broken. Ci bond. So what's the cost for that? Based on the book. Is there does anybody have the book? Yeah, you guys have, right?
Oops.
I really don't know the number.
I have
Yeah.
methyl attached to it.
Yeah, so you can take the methyl iodide. You can you can use that. It's an approximation, okay? Or is there another one? Is there like a one with a butyl? Yes.
Yeah. There's this one's CH3. Yeah.
Okay, and so that's a better approximation, right? Because what we have here is like an alkyl chain. We have a propyl chain, right? This is 1-iodo-propane, so 1-iodo-ethane is a better approximation for the bond strength of this carbon-iodine bond than a methyl attached to an iodine. You see what I mean? You take the thing which is closest to your actual compound in the table. It might not be the exact thing, but you take something which is as close as possible. Does that make sense? So let's take the ethyl one. How much is that, the cost?
222.
222, right? And then what's the number behind? Oh, that's in kilocalories per mole, I guess. Okay, so that's just say so that's kilojoules per mole. Okay, that costs us plus 222 kilojoules per mole to break. Now, what else is broken? What else is broken? The bond, the HBr bond, right? So we should have that in the table. How much is that? Do you mind telling?
368.
So that's plus 368 kilojoules per mole. So those are the costs. So those are the positive sides. Okay. Now, how much energy is released? So we'll say bonds formed. What is formed? We are forming a carbon-bromine bond, right? CBr bond. So do we have something like ethyl bromide in there,
Mm-hmm. That is negative 285.
Okay, so that will...
That's 285 with negatives and you subtract.
Yes, so we'll say that gives release is 285, right? Kilojoules, so I'll write down negative 285. So here's the trick, right? If we make this negative already here, we can just add up all the numbers in the end, right? If we keep it positive and we subtract it, so it's going to be the same. So we'll say negative 285. The other thing which is formed, what else is formed? The HI bond, right? So we have HI, the HI bond, and how much is that? 209. So that the release is 297, right? Kilojoules per mole. So now what is the sum of all these numbers? Overall, Then you need a calculator. Does anybody have a calculator? You can use your phone. Yeah. +8
Plus 8.
or -8?
Plus 8.
+8. Okay. I think that's correct. So +8 kilojoules per mole. So this is endothermic. Okay? Sounds good? So that's how you do this. You basically just sum up all of those energies. It's a good thing to know how to do this. Okay? It's helpful. Any questions? So we kind of did this together. If you guys want, if there's apples left in you can just pick them up. Let's do the next problem. You guys can do the next one. So this one, all right. Who wants to try the first one? So predict the sign of delta S for the following reaction. And then, so you get tired of you, Caroline. And then I'm slowly starting to know your names. I'm really bad at it.
Should I just do A and then?
Yeah, and explain why. It's not to explain why as well.
Okay. I think it's negative because entropy is decreasing. Like you're taking 2, making it into this one cyclic compound.
So you're taking 2 molecules, making 1, right? Remember I drew this container on the board where we had, the more different kind of molecules you have, the more the disorder, right? So the higher the entropy. And then you're going from 2 molecules into 1. It's like having 2 moles of toys in a room, and then you just make 1 mole of toys, and it's more messy with more toys. Okay? Does it make sense? Thank you. Mm-hmm. That was easy, Apple. I'll give you this one. Do you prefer if it's a yellow one or one of these? You're welcome. Thank you. Okay, so that's good. Any questions? Then the next one. Let's do the next one. Again, the entropy delta S for this reaction. Yes. You can do it. You can write it, and then you can explain it, so people don't always hear the same voice. You know what I mean? Mm-hmm. I'll give you an apple. They're all huge apples. There's a big lottery. All right. So it's positive because it's less ordered, right?
Mm-hmm. There's not more hydrogen atoms. I totally just made that up, didn't I?
Yeah, there's more hydrogen atoms. That's not right. But it's still positive. That's right.
Yeah.
But why?
Because it unfolds, so there's not as much structure to it.
I was doing like this. It's more wiggly, okay? It's less. The ring it has fewer conformations, so it's more ordered, and like this, it's more flexible. Exactly. Thank you.
Thank you.
All right, let's see. Where's the pen? Here we go. Okay, so let's go on. So they will get harder towards when we are going to do the... Okay, this one. This is more mathematical. Who wants to try this one? You want to do this one? I mean, you're an engineer, so you should be able to do this. So explain how you get the result.
Oh,
right?
okay. So I'm using the equation.
Yeah.
And then if I have a positive here and a positive... Oh, sorry, I did that backwards. Hold on. Where's the eraser? Okay, there we go.
Yeah, the easiest thing.
So if I have a negative... Oop, I still did that wrong. There we go.
Positive, yeah.
So if I have a negative here and a positive here, you still end up with a negative sign.
Always.
Because you have a negative subtracting a negative.
Yeah, so it's always going to be negative.
And
Exactly.
since delta G is negative, it means it's spontaneous.
Uh-huh.
And since it's spontaneous, that means it's going to favor the products.
Exactly.
So it
That's right.
so favors
It's actually pretty
products.
simple.
And then I'll just do reactants.
Your handwriting is getting good at that.
2 products.
Yeah. So whenever the delta G overall is negative, right? It's an exergonic process. And then that means it's... Thank you. So that means, yeah, so that's it. But you see, in this case, if the delta H is negative, it means it's exothermic. And the delta S is positive. That means it always favors the products. It can never favor the starting materials. Now, if the opposite is true, if the delta H is positive and the delta S is negative, then it will always favor the starting materials, right? So those are the easy cases. Now the difficult cases arise. The more interesting ones are when, when the delta S, for instance, is positive and the delta H is positive, right? Then sometimes, depending on what the temperature is, the reaction can be either spontaneous or not. You see, or if the reverse is true, if delta H is negative and delta S is positive, right? Then the two factors are competing. And those are the interesting cases. So then you have to actually plug things into the equation to solve it, okay? But you see, in this case, it's pretty straightforward. But remember this equation. That's really, really important, all right? Thank you. So let's move on here. Okay, this is a lot of chapter 6 stuff. What is the energy of activation for the following reaction? And what is the equilibrium constant? So without actually having to solve, the equation, we use this rule of thumb. See if you can. Who wants to try this one? You want to try? Okay. Then I can save an apple. I can save an, unless you want another apple, but
No, I don't want another apple. Thank you for offering.
You can start trading apples if you want.
Trading.
Sorry. Just making jokes here. So what? Yeah. This is the activation energy, right? So it's about 10 kilojoules per mole. What about the equilibrium constant? How did you calculate it?
Because if we look at it, we can see that the products have a lot lower energy, so the reaction's going to want to go to the products. And so I was like, oh, probably 99% of them will be at the products. And
so
then
how much lower are the products in energy than the starting point?
10 kilojoules per mole.
10 kilojoules per mole. Okay. So write down, so the activation energy is 10 kilojoules per mole, right? But now this is basically the delta. No, this will be the delta G, 0, right? Because you see, what are we?
Oh, free energy.
Free energy, right? So this is actually a tricky question. So write delta G 0, right? That's the reaction free energy. Remember, that's the difference between, right? Again, this is activation energy. It has nothing to do with whether it favors the product or the equilibrium constant. What has something to do with it is this part. This is the difference here, right? So it's here and here, right? This is the reaction free energy, which is the delta G0, which goes into the minus RT, L, and K equation, right? So now, what was the rule of thumb I told you? How many kilojoules per mole is a factor of 10?
6.
6. Is that right? Is that what I told you?
It was like every 6.
Every 6, yeah.
Yeah.
I know it in kilocalories per mole, so I think it's about every 6. That's right. So you said 10 to the 3, right? It favors the products, clearly.
Right.
But you see 10 to the 3 is a little off.
It's aggressive.
Because it's not 3 times 6. It's like 3 times 6 would be 18.
Right.
So it's more like...
Like almost 2 times 6.
Almost 2, so maybe like...
So like 10 to the 1.5.
Yeah, so like a 90, equilibrium constant is probably like 90. Does it make sense?
Mm-hmm.
Okay, so that's what I wanted you to do here. You did a pretty good job.
Is the delta
Thank
G
you.
minus or positive?
It is... What do you think?
Negative because it ends lower than it starts.
Yeah, exactly. It's negative. And how can you see? Because you do... The delta G is defined... Look, the delta G is defined as the free energy of the product. That's always the case. Minus the free energy of the starting materials. Okay, so now what's the free energy of the products here is 10, right? The free energy of the starting materials is 20, so 10 minus 20 gives minus 10, okay? And so it's negative, so that means free energy is released in the reaction, okay? So does that make sense? This looks like a really simple question, but actually, applying the rule of thumb and everything, it makes it a little harder. Yeah?
So how exact do you want us to be when it's like between, here, like it's between 6 and 12? Because we could, like...
Well, generally what I do in an exam is I'll try to get you something which is an exact multiple of 6. So it might be like 18, and then it's easier. If you get close, if you get pretty close, if you say between 10 and 100, that'll be good enough.
Okay, cool.
All right? Like if you're like guessing it, that's fine. As long as within a factor of 10, it should be fine.
Okay.
What I want to see is if you know that rule of thumb and if you can apply it. Look at the energy diagram or the free energy diagram and figure out how it all relates, right? Okay? Do you guys have any questions about it? Yes, please.
I wouldn't get the rule of thumb day, but I'm just learning it now. But does it only matter when does the rule of thumb only work when the activation energy is 10? Or it could be
Can be anything.
anything?
So
but
the
it's
rule
always-
of thumb goes the way it's the same, but it has nothing to do with the activation energy. It's the free energy of the reaction.
Oh, free. Okay.
Okay.
So it's
So it's the difference in energy between starting materials and products, or products minus starting materials. It's not, the activation energy has something to do with the transition state energy, right? The highest energy on top here, and this one doesn't matter. The activation energy. So it's the difference between products and starting materials. You see, so from exactly this one, and so that is related. So the rule of thumb comes out of the delta G equals minus RT ln K, where K is the equilibrium constant. So what we have, the rule of thumb is essentially whenever you have a difference of 6, whenever you change the free energy difference by this delta G0 by 6 kilojoules per mole, then it leads to a difference in factor of 10 for the equilibrium constant, because it's logarithmic. So, for example, if you have a difference of 0 in the delta G, so give me 1 second. Oh my God, what's going on? That's nothing. I keep getting these calls in Chinese. I don't know.
I do too. Yeah.
You do that too, and it's like, I don't know. It's like some scamming. My wife tells me. My wife is Chinese, so she can understand it. She's like, don't listen to it. It's like they want like your bank information or something. It's basically a scam call in Chinese. So you don't want to answer it. Sorry. Okay. So essentially, if you have a difference of 0, right, kilojoules per mole, the equilibrium constant is 1. All right, that's where you start. And then if you have plus 6 difference, the equilibrium constant, so that means the products are less stable than the starting materials, right? If you have plus 6 difference there in the delta G0, then the equilibrium constant will be about 10. Sorry, 0.1. Not 10, 0.1, right? Because it favors the starting materials. And then if it's plus 12, what's the equilibrium constant? 0.01, right? 10 to the minus 2. Okay? And if the equilibrium constant is minus 12, if the delta G0 is minus 12 kilojoules per mole, what's the equilibrium constant? 10 to the second, so 100, right? You see, that's what so if the delta G0 is like 24, right? Then it's 10 to the 4. Does it make sense?
Yeah.
Sorry, minus 24. Okay, that's the rule of thumb. And we went over it in class, like I wrote the table on the board. So I want you to be able to apply. This is a super useful rule, because it allows you to, whenever you see a free energy difference, immediately guess pretty accurately what's the equilibrium constant, right? It's a very powerful rule. I encourage you to know it. So, any other questions? If not, let's move on. This was probably good for people watching the video anyway, so you can go back, watch the rule of thumb if you forgot about it. Just like a podcast, okay, but it's still there. So this one, is the reaction exergonic or endergonic? Endergonic, right? What you look at, this is an easy one. So you look at the starting material and product energies, and you see like products, and you see that here this is the difference. Delta G, this is the delta G0 is larger than 0, and so that means it's endergonic. Okay, good. So we don't need an apple for this one, that's fine. I can eat the apple. Now this one, this is for you guys to draw in arrows. Who wants to try? You can pretty much just draw the arrows right in there. This is going to be, I love these kind of problems. I will, do this stuff on the exam too, where I'm going to give you like some mechanism you haven't seen before. Some easier ones, some harder ones, and I'm just going to ask you to draw in the arrows. Okay, very important skill, so that you can learn how to the book has a couple of these practice problems. I think that's super helpful. You can just like draw in the arrows. Who wants to try? You try. And I love to draw arrows in red. Just how I always do it. So I selected red.
Okay, cool. Let's see.
I'll get you like an apple while you start. Okay.
Okay, sounds good.
Perfect. So can you also comment, maybe you don't have to write it, but just comment on what kind kind of, if you know what kind of arrow pushing pattern we are looking at, you know, whether it's a proton transfer or a little sort of leaving group or...
Okay.
Try it. So
Okay.
you're not required to know whether it's a proton transfer or stuff like that, okay? I won't ask for that on the exam, but I think it's helpful for you to categorize things.
Okay.
All right.
I don't know if I know the names, but
Try it.
I have a general idea. So we're protonating the hydroxide
Yeah,
to get
alcohol.
yeah the alcohol to get water, and then water is going to be a better leaving group,
Yes.
and then
Why is water a better leaving group than hydroxide? Because H3O plus, remember, good leaving group has to be a strong acid, okay? Or the conjugate acid of a good leaving group is a strong acid, right? And H3O plus is the conjugate acid of water as a leaving group, and so it's a good leaving group, water, okay? But then what's the conjugate acid of OH minus? That would be the other leaving group, right? Initially, that one, the conjugate acid is water, and the pKa of water is like 17 or 15, so on that order. Okay, so that's a 16, and so that means that's really not a strong acid whatsoever, right?
Right.
Because the pKa would have to be below 0. So OH minus is never a leaving group. That's one of the worst leaving groups you can have. But when you protonate it, then it's a good leaving group. And did you guys do this in lab?
yeah, and
That's
then
what you
we're
did in lab,
replacing
exactly. So you protonate it, right? And that's exactly what's happening. Okay,
Yeah.
keep going. Sorry.
it. Okay, and then
Oh, you are done already. Okay.
yeah, and then we replace it with the
And then it's a nucleophilic attack.
Yeah.
Yeah. Here we go. So the overall thing, thank you. The overall reaction here. Does anybody know what the overall kind of mechanism is here? We haven't really learned it much in class, but this would be, you know, is it a concerted mechanism or not? It's a substitution reaction, right? Because you see the OH is leaving and then it's substituted by a bromine.
It's SN2.
So SN2 would be if it's concerted.
Oh, then it's SN1.
So this is SN1, okay? Because you see, you have loss of the leaving group first, followed by attack of the nucleophile, which is here the Br minus. Does that make sense? So this is an SN1 reaction. SN2 would be when the leaving group leaves at the same time as the nucleophilic attack happens. We kind of touched upon it, like we'll talk about SN1 more. Yes?
I have kind of a silly question, but both problems all made sense to me, but like the direction of these arrows, like I'm just like struggling to follow.
Which one?
Like so the top left, there's like the arrow going down, right? Down to the. So there's like this arrow, but then there's also this arrow. So.
Oh.
Yeah.
So here's how it goes, okay? Generally, that's what people do when they write mechanisms, okay? It just looks like this. So this part, look, what they write here, let me try to highlight this. What is written here, this part, is literally just, that's the overall reaction, okay? That's not divided up into individual steps. That's just showing what's happening overall. Like essentially on the left is the starting material, over the arrow is the reagent, and on the right is the product. Now what's all of the other stuff, like this thing, is essentially telling you how it happens. Individual steps, right? These are the micro steps, kind of the individual steps, going through all of the mechanistic steps which finally lead to the product. So this tells you how the reaction happens. That's why there is two arrows, but the overall thing is really just the thing on top is just like this thing is really just showing you what's happening overall. Okay, does that answer? Mm-hmm. It's often written like this. Okay. Why is it written like this? Because generally, this is kind of an intermediate level or still kind of a beginner level problem, because you just have to draw in the arrows. Okay, so what's going to be an advanced thing is a question like this where. Let's say I take out everything down here. Everything here is gone. And I'm just showing you the overall reaction. And the question will be, draw a mechanism for the following reaction. Which means you have to come up with the whole thing down there, including all the structures, all the charges, all the mechanisms, all the arrows, right? And not just the arrows, you know what I mean? In this case, I already draw out the mechanism and you just draw in the arrows. That's kind of it's just to get you guys started. Does that make sense? But that's why it's usually drawn like this. I'll give you an overall reaction and ask for the individual mechanistic steps. That's kind of the real deal. And you will see that. It will happen. Like on the final, we'll have some of it. And then the next semester, it'll be more and more and more, okay? Does that make sense? Mm-hmm. You will slowly learn how to do it. All right? So let me take off all the yellow. And I think we can move on to the next question. Did I give you an apple? I did. You already ate it. Yeah. So now you see this is actually something going in that direction now. So I'm giving you the starting material. I'm not even telling you what's the product. I'm asking you what's the product and how does it form, right? And so you have to, but it means draw a mechanism. That's the mechanism. Like you draw individual steps where you draw arrow pushing for each step. You're like, this happens first, then this happens, and here's the final product. Right? So who wants to try this thing? You want to try? Okay. It saves a lot of apples. You can have another apple if you want. That's fine. You might get a stomach ache if you eat too many. So you're drawing the product first, yeah? Okay, that makes sense. And that's the mechanism. That's it. It's good. Okay. Be careful when you draw the mechanism. Just make sure you point. So you're pointing it at the positive charge, right?
Yes.
You see the arrow?
Trying to point it like at the thing.
So point it at the carbon atom. Point it, rather, you see, I saw you pointed it onto the positive symbol. So the standard thing is pointed, onto the carbon atom here, where the positive charge resides. Okay? That's good. Any questions? You just make, why does it form this carbon? Because from secondary to tertiary, right? And the tertiary is more stable. Okay? Here, let's do this one. And the mechanism as well. Who wants to try? Okay. Let's see. I'll give it to you.
So I have two different ideas of what might happen, but I'll just
you can draw both of them.
So
and then we can discuss.
Yeah, sure. So my first idea is that it would move to something like this, where it would have like resonance.
Okay.
Stability.
How would that happen? Can you draw a mechanism?
Yeah. Also.
Let's draw a mechanism. Now we'll see.
This would go here, but so that doesn't violate the octet rule.
So where does it go? It goes like in.
Oh, that's kind of a bad arrow. It would go
so
to
that might violate. That will violate the octet rule.
But I moved the hydrogen. So
oh, you moved the hydrogen at the same time.
Happen. It's kind of a weird thing.
Sometimes these kind of reactions actually can happen, but they're fairly rare. Okay.
Okay.
I'm not sure if it would happen in this particular case, but sometimes you can move hydrogens and stuff. But no, this is very complicated. Okay, so it's not the most straightforward thing.
Okay.
Whether on an exam, I would carefully think about whether it's right. But if you write it, if it's actually a correct thing, which could happen, you know what I mean? And even if you didn't learn about it yet, might still give you points for it. All right, so I'm not going to penalize you for it, but for the sake of the class, this is a complicated thing. So we generally, if you move the hydrogen at the same time, it doesn't violate the octet rule, and then it might actually be correct. It's like a sigma. It's like a rearrangement reaction. Okay. But there's an easier solution. What was your second thought on how it could happen?
It was even more.
Oh, it was even more complicated.
I didn't actually think about the mechanisms of how this would happen. I just sort of went to
the product.
Yeah, and it's that, but then similar thing with resonance, but one would be tertiary, one would be primary. I don't know.
Yeah, that might work too, but it's complicated.
Yeah.
Okay, it's complicated. So let's see who else has other. So in general, my thought. Okay, pick what happens. Pick the simplest possible mechanism you can think of. Okay. Whenever you look at something like that, don't pick something super. Don't. The easiest way to figure out what's the product actually is you draw the mechanism first, and then look at what product you form. You know what I mean? Rather than just thinking about some product you might imagine could happen and then try to come up with a mechanism. That is harder. And if I give you the product, think about the simplest possible mechanism, not some. If it's too complicated, it will be. It is less likely to be correct. But I think what you actually drew is correct, to be really honest. It's pretty cool. So, who else wants to try? Who else wants to try? You try. We have very... if you do all the problems, it makes me feel like everybody can do the problems. And then it makes me feel they're all really too easy. Then I'll put harder problems on next time. But, you know what I mean? I realize it's always better doing the problem.
I'm so sorry.
That's fine. All right. So hold on, where do you start the arrow?
At the electron pair.
At the electron pair, and there's no electron pair where you started it, right? So you started. Where's the electron pair? The electron pair is the CH bond. Okay. So you move. You start from there. Yes. Yes, and that's it. It is just one arrow, one powerful arrow, which on the exam might give you 5 points, 6 points. Why does it happen? You see, why does it? It's just a CH. It's just basically a hydride shift, right? And a hydride shift. That's how I would call it in lecture. And why was it called hydride shift? Because a hydride equals H minus. Okay? You see here what's moving is basically formally an H minus, right? You can see that? And why does it happen? Why does it rearrange? By resonance, right? You see you're going from a secondary carbocation, which is not resonance stabilized in the starting material here, to a secondary carbocation, which is stabilized by resonance. Okay? I mean, I can draw you we should probably draw those. I will draw them upside down, which is not my favorite thing to do, because we have space. You see, this is the other resonance structure here, right? Here's the other resonance structure. Beautiful resonance structure, okay? So we go to a resonance stabilized carbocation, which is more stable than the non-resonance stabilized one. And the structure you drew also was resonance stabilized, so it was actually was a good. Your answer was a good one. Okay. Any questions? So you guys practice this stuff. Okay. Practice it. So now, curved arrows, new reaction. You haven't seen. You will see it's carbonyl addition, some nucleophile adding to a carbonyl aldehyde. Okay, here's an aldehyde, right? There's a hydrogen which is not drawn. There's another hydrogen here which is not drawn. This is a product. So it's basically a nucleophilic addition. Who wants to draw the arrows? Then not you. Let it go with somebody else. Otherwise, I have to bring all these apples home. Thank you. No, and here's the deal, okay? I mean, I'm recording this stuff, but I'm not mentioning your names on the recording, right? So there's no way, except Caroline. So there's no way to identify you, even if you do it wrong, okay? So the whole point is to get it wrong now, and then get it right in the exam, right? So it's your chance to put down your answer, and we can discuss. All right, it's like a huge, and you will feel more alert if you get it wrong in like a place like a review session than if you do it like at home and you practice it. You know what I mean? Because it's an enormous learning effect. Believe me. Okay? So feel free to volunteer, even if you're not 100% sure your answer is correct. Okay? If this is absolutely correct, this is great. Okay? Thank you very much. I gave you like the biggest apple I had. All right? So we are almost done, actually. This is probably going to be a short review session, which is fine because it's Halloween. Okay? So, I mean, I can make up more problems on the fly if you want, but we can probably.
Do you need to draw on the H's?
Hold on, let me go back.
Sorry. When you do number 9, like, should I draw on those H's?
You mean the ones I drew in? No.
Okay.
No, you don't need to draw them. I just threw them in because I'm looking for something to talk about. You know what I mean? I'm like a talk show host, kind of. I just say something and then I draw something in there. Okay? Because otherwise, if I wouldn't say anything, we would be done with these problems in 5 minutes, and then it's like a waste of your time to come here. Does it make sense? But you don't have to draw those H's.
Okay.
I think it can be helpful for you to see. If you draw them in, it helps you to see that they are there, so you don't violate your octet rule, with arrows, potentially. All right, so this one, it's a little bit longer one. So the last one, I think. Who wants to try? Who wants to try? You want to try? Yeah. Good. Let's see. Here we go. Do you want another apple?
Oh no, that's okay.
Good. So loss of a leaving group, rearrangement. Yes, and then this is a resonance arrow. You guys see that? So that's formally a resonance arrow, right? And yes, that's good. So generally, we shouldn't actually draw it this with the. I mean, that's not your fault. You know what I mean? Generally, the better way to do it is just draw a base, some sort of a base. What's the base here? What do you guys think is the base here? I just didn't draw. The base would be, what is it? What do you guys think?
The water.
The water, exactly. So it's the OH2, right? Because we lost water before, so there clearly is water left, right? So you draw it like this, it's better.
Okay.
If you just lose the proton, it means you lose H+, and that never happens. It's always picked up by a base, right? So this is good. This is very good. Now the only other thing... Yeah, so you see in terms of notation, this should really be written like this. Because these two are, you see these two guys here, these two are really resonance structures of each other, right? They're not actually, it's not a reaction happening, it's just resonance structures. So we should put them into those brackets,
Okay.
right?
So on an exam, we should be sure to do that.
Well, yeah, but I already drew it like this, so it's just, I took it from some book or something, so that's why. But just to be pedantic. On an exam, you should draw it like this, that would be better.
Okay.
Yeah. Any questions? So we'll do more. Next week should be all SN1, SN2, the whole chapter 7 deal. So that'll be a really important review set. Is that the last one before the exam, or is that? No. Yeah. Huh? Yeah. Oh my goodness. Is it?
No, I hope not. I hope you're joking. No,
I don't think I'm joking. I looked at the. No, I mean not today's. Like the next week one.
The exam is the 15th. 14th. Yeah, that was our last week.
So next week is the last review session before the exam. So there is literally literally next week, and then we'll do all the SN1, SN2 stuff, and then we are done, and then the exam is the week after. Okay? It's like a pain, I believe me. But just keep practicing. Okay, that's what I'm saying. It's like I hate to make another exam. It's so short. No, but otherwise the reason is otherwise it would be after Thanksgiving, and then it's like, that would be then it's like too close to the final. It's just a short semester. Okay. All right, keep studying. Thanks, guys.